All right, so today we're going to go over what is the second last concept in this unit. We've got conservation of energy, which, good news, all review of Science 10. Okay, the principles of the law of conservation of energy, of mechanical energy, are no different than what you learned last year. You will do basically the same kind of questions you did last year because there's really not any other way to ask them. Okay, we will look at, in Unit 4, a different kind of potential energy. Okay? In this unit, we're only going to look at gravitational potential energy, but in Unit 4, we will do some law of conservation of mechanical energy stuff involving elastic potential energy, like the energy stored in a spring or a stretched rubber band or things like that. Okay, but for this one, for this unit, because we haven't done anything with elastic energy, we're just going to focus on gravitational. Okay, the other thing we have to cover, and we'll cover it probably tomorrow, is power. Okay, power is pretty straightforward. It's easy. And you actually don't have to do any calculating to do with it. You just have to understand what it is. I also today put on your Google Classroom the unit exam review package. Okay, so that is on there now, and I will do a unit exam review probably on Thursday. Okay, so we'll do our official kind of review period on Thursday of this week. Okay. All right, so first thing we have to understand, energy cannot be created or destroyed, okay? That's the law of conservation of energy. Energy can't be created or destroyed, but it can be transferred and changed. That is, altered from one form to another, right? Sometimes that makes it look like it has been lost or destroyed or whatever, but it hasn't, okay? It's always still going to be there. Okay, for those of you who have an earbud in one ear, holy crap, take them out right now. Okay, I need both your ears right now. Okay, understand that energy can be converted from one form to another. The most common thing, or the most common transformation, would be that it is going to go from mechanical energy of some kind into heat. Right, that's the most common place where energy appears to get lost. Okay, and we're going to use this concept to calculate other variables related to the mechanical energy of an object, just like the roller coaster questions you did last year. Okay, you find out that the roller coaster is on a hill that's this tall and it's going this fast. Calculate how fast it's going when it's this far from the bottom. Okay, stuff like that. Okay, so there's two kinds of energy. We've talked about them already in this course, kinetic and potential. Okay, together they make up mechanical energy. When we add an object's potential energy and kinetic energy, that gets its mechanical energy. That includes elastic potential as well. Okay? It also means that if there are any non-conservative forces, they could make it appear as though the energy is lost from the object. And that's what we've been dealing with up until now, is when there are non-conservative forces. We've been using this formula, which is the WorkEnergy Theorem. Any work done against non-conservative forces causes EF and EI to be different. If there are no non-conservative forces, then no work is being done, and these two numbers they're equal, right? So in any perfect utopian system or isolated system, the initial mechanical equals the final mechanical. Obviously, everywhere else in reality, that's not the case, and there's going to be either work getting put in and the energy increases, or work done against non-conservative forces and the energy decreases. Right? Everybody okay with that idea? All right. So if we're looking at a roller coaster, okay, at the highest point on a classic roller coaster, okay, we would have high potential energy and low kinetic energy. High potential because we are far from the bottom. Good, nobody said high. Usually someone says high and then people chuckle. We're not. We're far above the ground. Yeah. Okay, so we're far above the ground, meaning we have lots of potential energy. Okay, usually at this point, we're also moving slowly. That's why we have low kinetic energy. Okay, and then as the cart goes down the hill, the potential gets converted into kinetic. That is gravity doing work on an object. Gravity does work. It doesn't change the mechanical energy. It just converts it from one form to the other. Okay. So if we get down here to the lowest point, that's where we have minimum potential energy, or maybe none, and our maximum kinetic. All right, so when you ride the Mindbender, okay, at West Edmonton Mall, this is the experience you'll have. You'll be towed up to the highest point on the ride, okay? And that is where you'll have lots of this and very little of this. and then you'll go down the first hill, which is the steepest hill. It's the longest drop. Okay, you go from moving at about like 2 meters per second, probably even less than that, to somewhere in the neighborhood of 25 meters per second in about 2 seconds. Okay, because it's almost straight down. In fact, it is straight down, okay, off that first hill. So you accelerate very rapidly, and you very rapidly convert potential energy into kinetic energy. All right, and it's a lot of fun, unless the roller coaster stops right at the very top, which it's only done once in our time there, but it was scary because it stopped, and we're just looking over the edge, going, funny. Not funny. Okay? And they just held us there. No one told us anything. No one came over the speakers saying, oh, we're just doing whatever. The roller coaster just stopped at the highest point on the ride, the most dangerous place, and left us there for 10 minutes. Nobody said anything. You should have seen the kid next to me. He had pulled like a Mel Gibson / Harry Houdini. He had almost dislocated his shoulder and was out. He was getting out. Okay? I'm like, where are you gonna go? Look around you. Like, it's one step to the bottom, dude. Stay on the car. I had to actually hold him in place because he had like wriggled himself. His torso was out of the harness. I don't know how he did it. It was like this weird contortionist thing. Okay, but he wanted out of there like nobody's business. I wanted out of there too, but where were we going to go? And it's not like, I mean, there's a set of stairs that you can walk down, but we were past them already. We were screwed. And then all of a sudden they just went beep, and down we went. It was the quietest Mindbender ride ever. Everyone was too afraid to scream. We had no idea whether it was just going to go off the tracks and we were all going to die because nobody told us what was wrong, ever.
Does that mean the kid was out of his harness?
He would, like, there's a seat belt, and then there's a shoulder harness that comes down. I pulled him back in when I noticed he had gotten himself out. I'm like, sit down. Are you nuts? Yeah. So he was like, yeah, kind of half in. He was all good though. Yeah. A little scary though. All right, so if we go up any other ones, then yeah, we're going to have, low potential energy, high kinetic energy if it's low. If we're going back up, like on the Mindbender, the second hill is about 7 or 8 meters lower than the first one, okay? And obviously you would have less mechanical energy there because along the way, you've lost energy to friction, right? If you ever listen to the Mindbender amid the screaming, it makes a lot of noise just in and of itself, okay? Sound's a form of energy. It loses a lot of energy to friction along the way. Okay, so in other words, our final mechanical energy in a utopian system where there's no energy lost, okay, initial and final are equal. So the total mechanical energy remains constant along the path between the 2 points. So if we're going this way here, okay, we're going down, we're converting potential into kinetic, and we go through the loop, we're converting kinetic back into potential, and then back into kinetic, okay, then back into potential, back into kinetic, and then a little bit of potential, okay, back to kinetic, a little bit more potential, back to kinetic, okay, as we go along. Everybody okay with that idea? All right. Okay, so there's ways to kind of harness this. And this is one of the ones that I saw. So this was like track and field provincials in like 2005. So a long time ago, but still, they still use this thing. It's a ramp. That's not what's cool about it, okay? I know you're looking at this going, Coder, you got excited about an inclined plane. Yes, I did. Here's why. Okay, this shot put return device was designed, I found out, by the Faculty of Engineering at the U of A. I know you're thinking they had to use like engineers to design a ramp. Yes, they did, because if you put any shot put at the top of this ramp, it will roll down the ramp. That's not the cool part. Okay, and it'll roll along this track. What will it do as it rolls along this track? Slow down because of? Right. And when it gets to the end of this track, it is right in the throwing area, and it comes to a stop. Okay? So what they did is they figured out how much friction there was along the track and made sure that they built a ramp that was just high enough to give the shot puts enough energy so that when they got to the bottom, they would roll along this and come to a stop at the end of the track. It works fine if you just put the shot put on there. Most people, though, they do this and they give it a little help. Then it rolls off the end. Then people's fingers get hurt, toes get hurt, like at the bowling alley, right? And you reach down and grab the bowling ball, and the next one comes in and smashes your fingers in between. You don't have to worry about that with this, okay? It's designed so that the amount of energy imparted to it by lifting it to here okay, is going to be all used up against friction along the track. Okay, so there's practical applications of that. Sorry, Kate. It just allows them to return the shot puts like without having to roll them along the ground, get them all dirty, right? Like, I mean, they got to get cleaned anyway, but it's just the most effective way to get it back, right? And not having people throwing it back or whatever. It's safe, right? You roll it along the track, everyone knows where it's going to go. Yeah, I know it looks elaborate, right? But I mean, because I'm a geek, I went over to the tent and I grabbed everybody on the team, like, you got to come see this. And they're like, what? And they thought it was something really cool, and it was, except they didn't understand. Okay? They didn't understand just how much of a nerd Coder is. Okay? I'm like, look at this. And they're like, what? Don't you see? And I had to explain just what I explained to all of you, to all of them. And they're like, Coder, you're such a geek. And they all went back. That's okay. I'm comfortable with myself. I know who I am. Okay, other practical applications. If we don't do this right, okay, if we have something like this and we don't do it right, then we might have too much or too little kinetic energy at any given point. And that happened in 2010 at the Vancouver Olympics. Okay, one of the skeleton racers, he was killed on the opening day during a practice run because the amount of friction on the skeleton track was a lot lower than they had anticipated it being because they'd gotten some rain, and so the ice was much shinier or smoother. And as he came down on the first corner, he had way more speed than they thought anyone would have, and he went up and out of the track, and he was killed because he went over the edge. Okay, now you've already built, engineered, designed this whole track, okay, around this stuff. Now you can't use it. So how did they fix the problem? No, they just started everybody lower. I mean, if I start everybody lower, they're going to have less energy when they get to that corner, right? So they just had to have a shorter run, okay, in order to make up for that. But it was certainly a big problem. I mean, the person was killed because they didn't anticipate that there'd be so much less energy lost to friction because of those conditions. Okay, so figure below shows that for any like bobsled, skeleton, luge, whatever, okay, runs that are going to happen, okay, if it's a perfect system where no energy is lost to friction, then this number, the total mechanical energy, remains the same all the way to the bottom. What changes is how much of it is potential and how much of it is kinetic. So as we move down the track, we lose potential, but we gain kinetic, and eventually it's all kinetic when we get to the bottom. No. Yes, but now that's going to be, they put on the brakes, friction appears, and then work is being done. Yeah. All right, so in this case, only gravity does any work, and it's only converting potential into kinetic. Yeah, once we get to the bottom, we put on the brakes, then yeah, we're doing work against friction, transferring energy out of the system. All right, I want you guys to try this one. Okay. I think we watched the video on this one. We watched projectile motion, right? Evel Knievel jumping over, or Robbie Knievel jumping over the Grand Canyon. Pretty sure we did. No? Okay, well, we'll watch it again. But first, try this, okay? This is a question based on something a guy actually did. Jumped over the Grand Canyon on a motorcycle because, well, he had nothing better to do. Okay, so what we know is that on the first side of the canyon, he was 70 meters above the bottom of the canyon, moving at 38 meters per second. When they land on the other side, they're 35 meters lower. You don't jump from the low side to the high side because then you do this, okay? And that's not good. So, okay, they jump from the high side to the low side, and then what we want to figure out is how fast were they going when they hit the ground on this side, all right? Assuming there's no friction, all energy is conserved, calculate VF. See if you remember how to do that. It's just like a roller coaster question from Science 10, all right? What we need to remember is that our initial mechanical equals our final mechanical. Okay, see if you can calculate VF. I'll give you a couple minutes on that one. Oh, a long time ago. We first have to indicate that in this case, our initial and our final mechanical energies are equal. On the initial side, he is 70 meters above the bottom of the canyon and moving at 38 meters per second. So he does have both kinetic and potential energy initially. And he also has both at the end because he's still 35 meters above the bottom of the canyon and he's moving much faster, most likely, on the other side. All right, so we would have EP final plus EK final. All right, everybody with me so far? All right, what I'm looking for, final speed, is part of this term. So I'm going to get that term by itself right now, before I plug in all the formulas and have to move more stuff. I want to get that thing by itself right now. So what do I do with EPF? Right, I subtract it over to the other side. Because really what I'm saying is mechanical minus potential equals final. All right, so I'm going to have EK initial plus EP initial minus EP final equals EK final. All right, now I'm going to punch in my formulas. So I'm going to have 1/2 mv initial squared plus m times g times h initial minus m times g times h final equals 1/2 mv final squared. All right. They never told me the mass of the motorcycle. Does it matter? No. Gravity is doing all the work, and all things accelerate at 9.81 meters per second squared. Therefore, it doesn't matter what the mass is, it would be going the same speed regardless at that point. That's the physics explanation. The mathematical explanation is that mass is in every term, so it affects every term equally, meaning it can cancel out. All right, so I'm going to get rid of the mass right now. It's one less thing I have to deal with. So 1/2 VI squared plus GHI minus GHF equals 1/2 VF squared. I can only cancel mass if I'm looking for an H or a V, because those two things don't depend on mass. If I'm looking for, if they asked me what's the final kinetic energy of the motorcycle, I would have to know the mass, because mass is part of energy. Everybody follow me there? All right, I want to get VF by itself. What do I do with the half? Divide it over to this side. All right, and then what? Then I square root. Okay, so I'm plugging in my numbers here. So I'm going to have 1/2 times 38 squared, that was the initial speed of the motorcycle, plus 9.81 times 70, the initial height of the motorcycle, minus 9.81 times 35, the final height of the motorcycle, divided by 1/2. And then I'm going to square root all of that. So square root of whoop, bracket that. All right. When they hit the ground on the other side, they will be moving at 46 meters per second. Actually, I think it'd be 46.2. I think we had 3 significant figures there, but no, I can't cancel out the halves because it's not in every term. There's an addition and subtraction operation on the top, so I can't divide the halves off. Okay. All right, questions on what we did there? Kelvin. Oh, I don't know why. It's a typo. It's a typo. Okay. Everybody all right with that? Okay. So this is what we just did here. Okay. So we launched it over. Okay. And then we've got our math here that we already did. All right. So we're going to look at kind of a few examples of this, just make sure we understand kind of how it works, review what we did and what we learned in Science 10 with it. Okay. And that'll kind of be it. We don't really need to spend a lot of time on something that's already effectively reviewed for us. Okay. All right, so we'll look at this one together. Okay, this one's going to illustrate why mass is important. Okay, why it doesn't cancel in some cases but does in others. All right, so we have a frictionless roller coaster car with a mass of 800 kilograms. At one point on its journey, the car has a speed of 4 meters per second. All right, so here's our roller coaster. All right, moving at 4 meters per second. okay, and is 35 meters above the ground. Later, its speed is measured to be 20 meters per second. All right, so that's, I'm going to say like over here. Okay, how do I know it's lower if it's moving at 20? It's faster. It has to be lower if it's going to be going faster. All right, calculate its total mechanical energy relative to the ground. Okay, so how do I calculate mechanical energy? EK plus EP. Remember, mechanical energy is the sum of both kinetic and potential energies. All right, so the mechanical energy at any point on the track can be calculated as long as I can calculate kinetic and potential energy, which I can. All right, so I'm going to have m times g times h plus 1/2 mv squared. All right, so that'll be 800. I can't cancel the mass here because I'm looking for an energy type. I won't get joules if I get rid of the mass. Okay, times 9.81 times 35 plus 1/2 times 800 times 4 squared. All right, so this is going to calculate the mechanical energy here and here and here and here and here and anywhere on the track because it's the same. It's conserved. Okay, it says it's a frictionless roller coaster. Okay, so therefore energy is conserved. Okay, all along the path. Okay, so we've got 800 times 9.81 times 35 plus 0.5 times 800 times 4 squared. All right, so there's our potential, or sorry, there's our mechanical energy. No, it isn't, because I missed something. That's better. Okay, so 281,080 joules, okay, is my mechanical energy anywhere along this roller coaster track. All right, so everybody follow what I did there for part A? Yeah? All right, now it says, what's the gravitational potential energy in the second instance? So they want to know what's the gravitational potential energy here, right? So I already know, okay, I can calculate how much kinetic energy it has. I already know how much mechanical energy it has. So can I find its potential? Yeah, this formula still applies. It's just now I'm dealing with the final numbers. Okay, so instead of looking for this piecemeal, okay, I'm going to do this, and I'm just going to say the mechanical energy, which is a number I have, minus the kinetic energy equals the final potential. I don't need the m times g times h because I'm not looking for any part of that right now. I'm looking for what the total potential energy at the end is. All right, so I'll take my 281,080 joules, okay, and subtract 1/2 times 800 times 20 squared. All right, so that means that at that point, I have 121,080 joules worth of potential energy. Could I calculate how high above the ground it is? Yes, because I know that this number is the potential energy. So it equals m times g times hf. And I would just divide it by m times g. Right? So it'd be 15 meters off the ground at that point. All right, everybody okay with that? Okay, I want you guys to try, for right now, just 1 and 2. We'll talk about 3 when you're done 1 and 2, because number 3 is going to require you to remember some stuff about projectile motion. in order to solve it. All right, so try 1 and 2 for now, okay, and then we'll talk about those, and then we'll talk about number 3. So the quick thing with number 1 here, guys, is if we have a ramp, okay, and something is sliding down it, it says it's frictionless, right? So it's an isolated system. That means it's frictionless, right? Then all of the potential energy this block has is going to turn into what as it slides down? Kinetic. All right. So it loses 650 joules, but that 650 joules becomes kinetic. So I take the 650 and add it to the initial kinetic energy of the box, meaning I now have 900 joules worth of kinetic energy at the bottom of the ramp. Okay, everybody all right with that? Right, it's all becoming kinetic, so that's all there is to it. How many people have done number 2? Okay, I'll give you a couple more minutes on number 2 here, okay, and then we'll talk about it and number 3. Okay, let's have a look at number 2 here. So I have a mass of 55 kilograms and it's 225 meters above the ground with a velocity of 36 meters per second down. All right, they don't really tell me what the context of this question is, so I'm just going to assume it's falling because they don't tell me it's on a track or anything like that. I'm just going to write that its initial height is 225 meters. Its initial speed is 36 meters per second. Okay, and I'm trying to find its final speed when it is now only 115 meters above ground level. All right, and it tells me use conservation of energy. So if it says use conservation of energy, that's what I'll do. Okay, that means that EI and EF are equal. Okay, and I'm plugging in for this. M times G times H initial plus 1/2 MV initial squared equals M times G times H final plus 1/2 MV final squared. I'm looking for this. All right, so what should I do with MGHF right now? Yeah, subtract it over to the other side. So I'm going to have MGHI plus 1/2 MVI squared minus MGHF equals 1/2 MVF squared. What can I do with M? I can cancel it. Okay, I'm not being asked to calculate an energy. I'm being asked to calculate a V or an H, which is not dependent on the mass of the object. So mass is going to cancel, which is good because they never told me what it was. Or sorry, they did tell me what it was, but I don't want to use it because it's extra numbers to punch in. Okay, so now I just need to divide both sides by 1/2 and then square root. All right, so when I'm plugging in my numbers here, I'm going to have 9.81 times 225 plus 1/2 times 36 squared minus 9.81 times 115 divided by 1/2, okay, and that will give me my VF. Whoop. All right, so at 115 meters, it'll be moving at 59 or 58.7 meters, 58.8, sorry, meters per second, and that'll be its speed. Okay, everybody all right with that? Okay, so just same as a roller coaster question, right? Nothing different than what you would have done last year in Science 10. Now, number 3, on the other hand, is different than what you would have done last year in Science 10. You have to remember some stuff about projectile motion for this one. Okay, so human cannonball at the circus is shot at a speed of 21 meters per second at an angle of 20 degrees above the horizontal from a platform that is 15 meters above the ground. Okay, if the acrobat has a mass of 56 kilograms, what is his gravitational potential energy relative to the ground when he is at his highest point in the flight? All right, so we would have to figure out how high above his initial point he ends up. Okay, we have to remember that when he is at that point, only his vertical speed is 0. He's still moving horizontally. Okay, and we would have to figure out exactly how fast that would be using something we would have found very easily when we were doing projectile motion. Okay, so what we're looking for here is the gravitational potential energy at their highest point, and if the net is 2 meters above the ground, how fast is he traveling when he hits it? So looking for a VF there. That part actually requires no projectile motion in order to do it. Part B is just like a roller coaster question, but part A requires some projectile motion stuff in order to be done. All right, so I'm going to give you guys a little bit of time on that to see how much of that you remember. Okay, you might have to do a little bit of trig, like finding vector components in order to do part A. Okay, give you a bit of time on that one. All right, so first thing I want to do on number 3 is calculate the mechanical energy of the human cannonball, because I can do that right off the bat. I know how high above the ground they are, I know their mass, and I know how fast they're going. Okay, it doesn't matter whether that's angled or not. Remember that this is speed. Energy is scalar. Okay, so it doesn't really matter whether it was fired at an angle or not. All right, so the first thing I'm going to do is calculate the mechanical energy at any point in the flight of the human cannonball, because this is a conservation of energy question. This number will be the same everywhere. Highest point, initial launch, when he hits the net, same number. All right, so I'm going to go m times g times h initial plus 1/2 mv initial squared and get my mechanical energy. So we know they're 56 kilograms times 9.81 times 15 meters plus 1/2 times 56 kilograms times 21 squared. That was their projected speed. All right, so 56 times 9.81 times 15. Plus 0.5 times 56 times 21 squared. All right, so there's the mechanical energy of the human cannonball at any point in their flight, 20,588.4. All right, so that's one piece of useful information. Okay, so we're looking for their gravitational potential energy relative to the ground when they're at the highest point in their flight. Now, I could go and try and find what their maximum height would be, but I don't want to do that. It's more steps than I really want to do. When they're here at their highest point, they're only moving which way? Horizontally, for at least that instant. Can I figure out what his horizontal velocity is using what I learned in the last unit about projectile motion? I can. If I have that number, can I calculate his kinetic energy at his highest point? Yes, then I just subtract that from the number I calculated, and I'll have his potential energy at the highest point. I could, like I say, find VI, then, know that VF is 0, calculate the height, add it to 15, but it's a lot more work, right? If I just find his kinetic energy at that point, it's a lot less work, okay? So that's what I'm going to do. This angle here was 20 degrees. Okay, and we know that this was 21 meters per second. So I'm just going to go cos of 20 times 21. Right, there's the speed of the human cannonball at his highest point. So I'm going to take that and multiply it by, so 0.5 times 56 times that number squared. There's the kinetic energy at his highest point. So I'm going to take my 20,588.4 and subtract that number, because that's the kinetic energy. And now I'll have the potential energy, 9.7 times 10 to the 3 joules. Okay, everybody all right with that? So you had to remember a little bit about projectile motion, but not much. You just had to calculate the horizontal component of their velocity. Does everyone understand why I did that? Okay, remembering that at this point, right, VF vertical is 0, so they're only moving horizontally, but they are moving, so they do have kinetic energy. All right, for part B is much easier, okay? I know the mechanical energy of the human cannonball when they hit the net, all right? So I'm just going to say that the 20,588.4 joules equals EP final plus EK final, right? I'm looking for how fast they're going when they hit the net, so I'm going to subtract the final potential over. So I'll have 20,588.4 minus 56 times 9.81 times 2. because they're still 2 meters above the ground level when they hit the net. That's going to equal 1/2 mvf squared, right? So I just divide both sides by half of m and square root, and I'll have my vf, okay? Same as any other roller coaster question kind of thing. Is that ringing a bell for everybody? Okay, seeming familiar? All right. Tomorrow we'll talk about power, how you get it. No, we won't. But, okay, that's what we'll be talking about tomorrow.